Our dynamic universe. The key areas covered will be work done, potential energy, kinetic energy, and power in familiar and unfamiliar situations, and the conservation of energy. What we will do today is revise the conservation of energy from National 5, state the law of conservation of energy, and carry out calculations of conservation of energy using formulae for work done, potential energy, and kinetic energy, as well as power. Conservation of energy. The total energy of any closed system is conserved, although energy may change its form. For example, energy lost as it changes to heat, light, sound, etc. These are the two equations you will need to know. EP, so potential energy, equals mgh, and EK, kinetic energy, equals a half mv squared. Also, work done equals force times displacement, which we write as EW equals FD. Energy and work are measured in joules. Combining potential energy and kinetic energy to find velocity. Using the conservation of energy, we can combine the equations for potential energy and kinetic energy to find a value for velocity, v, without needing to know the mass. First, let's write down our equations for potential energy and kinetic energy. So EP equals mgh, and EK equals a half mv squared. Because energy is conserved, we can say the potential energy is equal to the kinetic energy. And replace EP and EK with their own equations. So EP is mgh, and EK is a half mv squared. As we have mass on both sides of our equation, we can divide by mass on both sides and therefore cancel them out. We now want to rearrange to give V, and we get V equals square root of 2gh. Power. Power is the rate of transformation of energy from one form to another. Power is equal to energy divided by time. We can write energy as work done, so power becomes work done divided by time. Work done can be written as F times displacement, so we have power equals F times displacement divided by time. We know that displacement divided by time is the same as velocity, so we can write power equals F times average velocity. Power is measured in watts. A car of mass 1,000 kilograms is travelling at a speed of 40 meters per second along a straight road. The brakes are applied and the car decelerates to 10 meters per second. How much kinetic energy is lost by the car? Well, we know we need to use our kinetic energy equation for this, so EK equals a half mv squared. And to calculate how much kinetic energy is lost by the car, we want to calculate its kinetic energy when it's going at 40 meters per second and calculate its kinetic energy when it's going at 10 meters per second, and then take away the second kinetic energy from the first. So EK equals a half mv squared, which equals a half times 1,000 times by 40 squared. This is equal to 800,000 joules. Let's calculate our kinetic energy at 10 meters per second now. So EK is a half mv squared, which is a half times 1,000 again, times by 10 squared this time. This gives us 50,000 joules. So 800 kilojoules minus 50 kilojoules gives us 750 kilojoules there. This is an answer of D. The total mass of a motorcycle and rider is 250 kilograms. During braking, they are brought to a rest from speed of 16 meters per second in a time of 10 seconds. What is the maximum energy that could be converted to heat in the brakes? We know this maximum energy is going to be the whole of this kinetic energy that the motorcycle has. So we need to write down our kinetic energy equation. EK equals a half mv squared. This is equal to a half times 250 times by 16 squared. This is equal to 32,000 joules. Because the bike is brought to rest, this means calculating our kinetic energy afterwards, it's going to be 0, so we don't need to take away any number from this because we'd just be taking away 0. So 32,000 is our final answer, which is C. A van of mass 2,600 kilograms moves down a slope which is inclined at 12 degrees to the horizontal as shown. We saw this example a few lessons ago, and we can now do part C. The speed of the van as it passes point A is 5 meters per second. Point B is 75 meters further down the slope. Calculate the kinetic energy of the van at B. We worked out the acceleration of that van was 1.5 meters per second squared, so this is a value we will need to use. So to calculate the kinetic energy at B, we use our kinetic energy equation, Ek equals a half mv squared, but we need the velocity at B. We have the velocity at A, but this is what we need to calculate at B. So using our Suvat equation, S, U, V, A, and T, we have our displacement, that's 75 meters. We have our initial speed, that's 5 meters per second. We want to calculate our end speed, that's V. Our acceleration is 1.5 meters per second squared, that's what we worked out in the last question. And we don't know the time, but we don't need to use the time. We can use the equation V squared equals U squared plus 2AS for this. So let's substitute in our numbers. V squared equals 5 squared plus 2 times 1.5 times 75. And we get V squared equals 250 here. We could work out V, but we can leave this as V squared, as in our kinetic energy equation, there's a V squared, so we can just put this number in, it makes it much more accurate. So Ek equals a half mv squared, which is a half times 2,600 times our 250. Remember, we don't need to square that, it's already squared. And this gives us a final answer of 325,000 joules. Here is an open-ended question example. Some cars are fitted with a system that stores the energy normally lost as heat in the brakes. Estimate the maximum energy that could be stored as a car is decelerated to rest. Clearly show any estimates you make in your calculation and show your working. This would be worth 3 marks. One way of approaching this question is to consider the work done by the vehicle. So our work done equation is EW equals FD, but we need to provide estimates for the force and the distance. The distance, we could say the car travels, could be approximately 50 meters to brake. And to get to our force, we can use our force equation, so F equals ma, and again we need to provide estimates for this m and this a. So the mass, on average, could be 1,000 kilograms for a car, and our deceleration could be approximately 5 meters per second squared. So writing down our distance as well, we've got 50 meters there. First, we can calculate our force. F equals ma, which equals 1,000 times by 5. So we've got 5,000 there, newtons. Now we can calculate our work done. So that's force times distance. That's 5,000 times 50. That's 250,000 joules. But that's not our final answer. We've just calculated the work done in total by the car, but only approximately 5% of this is going to be converted into heat energy. So we need to write a sentence along those lines. So 5% of 250,000 joules is 12,500 joules. Another way we could approach this question is by using our kinetic energy equation. So Ek equals a half mv squared. Again, we need to give estimates for this mass and this velocity. We can take the mass again to be 1,000 kilograms and our velocity to be approximately 20 meters per second. This 20 meters per second corresponds to approximately 45 miles per hour, which we know is a normal speed for a car to be traveling at. So our kinetic energy equals a half mv squared, which is a half times 1,000 times by 20 squared, which is equal to 200,000 joules. Again, not all of this is going to be converted into heat energy, so we need to say that approximately 5% of it will be. So 5% of 200,000 is equal to 10,000 joules.